All right, we'll go ahead and get started. Hi, everyone. Welcome. Thank you so much for being here today. My name is Emily Rogers. I'm the Senior Marketing Manager at Kovalus Separation Solutions. Very excited to kick off our first session of our new series, Kovalus Webinars. For this series, we really aim to share practical knowledge and challenges that we found in the field and highlight key learnings across a wide range of markets and products. So this is our first webinar, and we'll have more to come in the future. Before we get started, just a couple of notes for the webinar today. The webinar is being recorded, and we will possibly publish this in the future on our website and YouTube channels. It'll also kind of help us learn how to make the webinar series better. Cameras and microphones are muted, as well as the chat feature at the top. We've disabled that. So for today, we're going to use the Q&A box. If you have any questions throughout the session, please put it there in the Q&A area. And then, like I said, we'll have a Q&A session at the end. Also, if anybody has any technical difficulties throughout the webinar, put that in the Q&A area, and our team will monitor that and we'll help try to get that resolved as soon as possible. After the webinar, you'll receive an email from Kovalus Communications. We have an email that we're sending to you that will contain a PDF technical white paper. So we've taken today's presentation and put that into a white paper format, give you a little bit of opportunity to dive into the content a little bit more, look at the graphs, things like that. We'll also have some other resources in the email as well. The webinar today could run a little bit long. We have a lot of content to cover. So if you have to drop off early or right at time, just put the questions that you might have in the Q&A area, like I said, and we'll follow up with you. We'll get back to you. All right, next slide. So today, before we get into the webinar, just wanted to provide a quick overview of Kovalus. Some of you may know us by our former name, Kovalus Separation Solutions. And we're coming up on our 2-year anniversary as Kovalus. With the rebrand, it's important to know that our mission has not changed. We've been a pioneer in the separation space since 1963, so we have over 6 decades of experience. As you can see here on the slide, we have a portfolio of brands that make up who Kovalus is. We have Kovalus Membrane Solutions. That's kind of the focus for today, across 12 different markets. We also have Relco, focuses on thermal separations, and Ecotech for ion exchange. So really here, from piloting to full-scale implementation after market sales and support, we do it all. And next slide. Also, the thing about Kovalus is we're global. So we have key regions across North America, Europe, Asia, beyond, and this allows us to work closely with our customers, providing local expertise and support. Next slide. And so for today, really what we're here for, what we're excited for, is the webinar on water savings and dairy membrane operations. I'm excited to introduce Saagar and Mike. Saagar is the Director of Process Engineering in the United States, comes with a wealth of knowledge. He'll be joined by co-speaker Mike. He's our Director of Process Engineering in Europe and Africa. He'll be facilitating the Q&A session. So yes, hope everybody learns a lot today, enjoys the webinar, and I think we're ready to get started. Thank you very much.
Thank you, Emily. Thank you for the introduction. I know good morning, I guess, for people who are in the States. Good evening for those of you who are joining us from other parts of the world. If you're joining much later, and if it's like way late night, I would thank you very much, because but yeah, overall, I think a few months ago we were talking about what is the topic we want to present, and unanimously, I guess, within our team, everybody was strongly voted for the water saving. So there is no doubt about the importance of water savings, water recovery that we're talking, and which is why I'm sure everybody here is also attending this webinar, because how critical it is. And as an industry, we're all trying to solve this problem, right? And for one of the reasons, when we were trying to do a Q&A that Emily talked about, we've kept the Q&A open-ended intentionally, because we want everybody to learn from each other. We believe that we're at a juncture of where the membrane technology is today. We're at a point where everybody is now striving for that extra optimization, and water is so important. So we kept the Q&A session open so everybody can see a question. And, everybody's problems are very different. When people think about water recovery saving, they think it's very singular, but actually it's very multidimensional. So we're hoping that everybody learns from each other. We learn from you, you learn from us, and we all are striving to make the industry and the water savings overall much better. So let's we have a lot to cover. So I've broken it down to seven major topics here, and we will cover each topic. Right. So quickly introducing the topic. So CIP rinse and rinse recovery. Essentially, what we mean when we talk about rinse recovery, what we're talking is not recovering the chemicals particularly. It's about recovering a portion of the CIP rinse itself. And we'll go into details. Second is chemical recovery. Chemical recovery is more like recovering the entire chemical. And of course, you get water along with it. And we'll talk about SelRO technology, but that will be very brief. We want to give you a perspective. Couple of the topics out of the 7, we will try to give you perspective. And one of the things here is low pressure versus high pressure systems. What is the difference? Why is it that plant engineers, plant managers, engineers across the board, whether you're our partners, our customers, everybody has to look at this slightly differently. Why is that important to see? Seal water reuse goes without saying. Trying to reuse seal water, we'll talk about. Product displacement and product flush, which is essentially trying to see if we can have a better way to displace the product and flush it out more optimally. And why is water coming into this perspective? We'll discuss about that. Of course, when we talk about water recovery, there is no doubt that you cannot avoid the topic of polisher RO, right? Using RO for water recovery. As an industry, we've done well trying to do polisher systems. But let's try to see what else is there that we can keep pushing ourselves towards. DF water optimization, which we'll touch upon if we have time, but certainly I think we should be able to quickly look through it. So covering those seven topics. So we're starting with CIP rinse and rinse recovery. The first topic, it's a little long, so I will try to dissect it into part 1A, 1B, 1C. So 1A is about rinse and using valves. So this is an example of a one-stage machine, let's assume, right? So you have a stage pump or a recirculation pump going to a stage, and you're trying to rinse, right? And when we talk about rinse, this is one stage, with a stage pump. But when I talk about rinse, I'm talking about the system being filled with chemicals, and we're using water to push out the chemical and out, right? But because we are working on a recirculation stage, we're working a recirculation style of operation. Dairies are all recirculation style, which means this baseline is connected back to recirculation pump. So what happens is when you rinse out, you're trying to rinse out the chemical and push the chemical out. Many times you get chemical sucked back into the stage pump or recirculation pumps. So therefore, what we're talking about is that it is useful to have a CIP drain valve, we're calling it, or you can call it CIP isolation valve. And then the other option is using a plug flow valve, either of these options. And what we've noticed is if you do rinse in and out versus using valves where it goes in, comes out outside, it does not go back to the baseline. We've seen that there is definitely about 30% optimization or water improvement. You can save 30% water. You can reduce the time of rinse itself. So now let's try to slowly take that learning and blow it up into like a bigger system and how it looks when you expand it, right? So I will take a half a minute to explain the different components of a big machine. Many of you are probably very familiar with filtration, and this is something that you know. For some of you may be newer or learning. I'm just going to give you a brief introduction, right? So you have a feed tank, you have a feed pump, and you have a baseline right here. And then you have stage pumps going to individual stages, right? And this can be stages 1, 2, 3, or you can say this is stage 1 to 3, 4 to 5, 6 to 9, and so on. The permeate from these stages come back to the permeate tank, and your permeate can be going from the permeate tank, the permeate can be going out to permeate storage. And because membrane filtration needs so much of CIP, you also have like a CIP pump, which can be used for CIPing the lines, right? So when we talk about, so that's a brief introduction of a stage, of a system itself. So when we look at this, essentially when we're talking about trying to put these valves, right? We're talking about putting plug flow valves, like we talked about plug flow valves. how they look in a big system, and then also putting CIP isolation valve or CIP drain valves, right? So going out and you rinse faster. Now that I've explained to you how the valves are, we will briefly talk about recovery during CIP rinse, right? So this is the part 1B, which we're talking about is we're trying to recover this rinse water using instrumentation. This instrumentation could be turbidity meter, could be temperature, could be conductivity meter. It's up to you. And it is something that you can install in the existing system. And that's a big advantage, right? You can say, there are some ideas that we're talking about today, and what can we do this in the existing system? Yes. Let's say you put in some meters like conductivity, turbidity, so on, and you say, okay, I'm going to now I'm going to go to the drain because I want to remind you, this is rinsing the chemicals, right? So now you have caustic. Let's say caustic is rinsing and it's rinsing out, and you're going to drain today, right? You're rinsing out the chemical, and what we're suggesting is, yes, put a meter and try to recover that into a caustic recovery tank, right? So, and when I mean by that, I don't mean that you have to rinse every bit of caustic. It's about, like, our CIP partners that also will understand. So we know the first, say 50-60% of the chemical is very heavy in soil. We don't want to recover that because we know it's dirty soil. We want to go to the drain, right? And then when we feel that the conductivity or the turbidity or the temperature is close to that of the inlet water, we want to go and capture that, and we call it as caustic recovery or caustic capture tank, right? So now we have to ask ourselves, okay, like, you're recovering the last 30%, but Saagar, there is heavy duty soil in the first CIP wash of a membrane system, right? So what we did is we are giving you a calculation, right? We said, let's go look at a 9-stage UF machine, and we say, okay, generally there are, say, 4 wash cycles or 5 wash cycles if you have a sanitize and so on. But we do, like, we are having a CIP pre-rinse, let's say a caustic rinse, enzyme rinse, acid rinse. The main thing to understand here is what we're saying is recovering the rinse water in the first 1 or 2 steps is probably not wise, because you want to clean the membranes. You want to keep your focus solely on recovering, cleaning the membranes. But after you have done the first 2 washes, the last 2 washes, which could be an acid rinse and which could be a final caustic rinse, that you're saying that I know it's 99 plus clean enough, which means the caustic and the acid in the last washes are fairly clean, which means I can probably recover more than 50, 60, 70% of that and reuse that, put it to an acid capture tank, put it to a caustic capture tank, and then reuse that as the next day's junk caustic or next day's acid step. And if you go about doing that, you'll find that I'm being very conservative here, to be very honest. It's like we're talking about this, but there is possibility that you can recover some of the final rinse in enzyme rinse, or at least in additional steps that we are doing rinsing, or even line rinsing, which we'll come to. But overall, there is an opportunity to save about 15% of the water. And we're not talking about reusing these caustic capture or acid capture as chemicals. We know that the chemical is going to be very low strength. So work with your CIP supplier and you might need to top up with more chemical, but the water is recovered. And just as a thumb rule, for every holdup of the machine that we've observed, you need about 2 to 3 times the amount of water to rinse out machines. I would say that if you're at 3, which I took some easy numbers here, but if you take 3, but there is definitely, when you do the instrumentation application, you can bring it down to about 2.5 times the holdup volume, and even more. But I'm just giving you a gauge of what we've seen. The next thing we're going to talk about, part 1C, is about rinsing the lines. Now, here I want to take an example. How do we recover the rinse during line rinsing now, or stage rinsing? So I'm going to take an example of an RO machine here. So it's all the same components like we discussed earlier. Over here, what we're talking about is, let's say, an RO machine. This is the same 9-stage RO machine. What happens is, RO machines don't have isolation valves like a UF and MF system. You generally have no extra, because it's high pressure valve and expensive, difficult to operate and under high pressure. So we don't have valves. So when you rinse out RO machines, what often happens is that you're rinsing out the chemicals going to permeate, and the concentrate is going to drain, the permeate is going to drain. But many times the first say first 3 stages already rinsed out. Let's say your rinse time is 10 minutes. In the first 3-4 minutes, the first 3 stages are get rinsed out already. And you still have to go through the entire rinse cycle to rinse out all the stages. What we're suggesting is if you put the right instrumentation on these backends, or in other words, if you have flow meters in these stages, you can tap into the conductivity of these flow meters or even temperature, which is available. So you can tap into the existing instrumentation you have, and you say in the first 3-4 minutes, I know I'm rinsed out in the first 3 stages. Just go back to the permeate tank and rebring that as water to rinse out the later stages. And therefore, you can save water, where because this is already rinsed out, it does not need to keep going through 10-minute rinse cycles. And also the concentrate, once many times the baseline is rinsed out. So if you use the conductivity or temperature, or even return back and reuse that water for rinsing. The next thing we're talking about now, it was multiple topics within rinsing, but we've covered the rinsing and trying to capture the water out of rinse steps. Next, we're going to talk about is the recovery of the chemical itself. Now, this topic, I'm going to keep it very brief. And the reason for that is, we wanted this webinar to be more educational upfront. We wanted to share knowledge. And chemical recovery is something that Kovalus as a company has done for many decades now. And SelRO is a technology that we have used where essentially what we're doing is that we can recover high strength chemical, pH of 0 to 14, high strength caustic, 10 to 20% caustic, that we are able to recover the chemical itself by removing the suspended solids, using NF membrane, which can take high temperature and high pHs, all range pHs, and the permeate that comes out of the NF membrane would be good strength chemical. And we are able to do this in multiple markets, not only for dairy, but multiple markets. And for dairy specifically, we have many installs in dairy evaporator processing, where it becomes a good ROI. But like I said, I don't want to spend too much time here. If you have interest in this, definitely reach out to your regional salesperson, and we'll be able to get you, collect all the right information so we can do an ROI calculation and provide you information on it. Chemical procedure. I know we have some chemical partners attending, and so we'd certainly like to talk about this. And as well, so Mike and I, we visited many plants, and often what we've seen is a plant is doing, let's take an example, a WPC 80 plant, and they're doing 4 wash steps, which is caustic, enzyme, acid, caustic. And then, we found that many times you go in a different plant, they're doing 3 wash steps, and they're skipping the first caustic because they have a good displacement or flush step, let's say product displacement step. And many other times we've seen that there is plants who are doing weekly or twice a week acids or once a week acids. So what we feel is that depending, and each plant is different, but we've often seen these things even for the same product that are sort of like adjustments in the CIP recipe. So work with your chemical supplier. Now, we certainly think there is a lot of opportunity here, especially in this example. We certainly feel that we've seen many times that acids can be done, say, once or twice a week in a WPC 80 process, and you go well with the alkaline caustic washes and enzyme washes. But it can be specific to the plant. It may be an issue that you had 2-3 years ago, and you're continuing to follow a full protocol. But trying to optimize the number of washes can give you 15 to 20% water savings. And of course, it's saving you time. Now, the same example can also be said about the RO, where we've many times seen permeate RO systems can have 3 washes. There are plants which are doing 4 washes. Some of them even do 2 washes with every alternate day, 3rd wash. So there are certain variabilities and opportunities there. Like I said, it's certainly something that you should talk to your chemical supplier, see if there are options, try to experiment it. And we're positive that you're going to see that there are opportunities to cut back a wash or make it more irregular than daily. Now we're going to talk about a third topic we're going to talk about today is low pressure versus high pressure systems. Now this topic, I would say, is more about giving perspective. Our intention of putting this particular topic was essentially, we've seen that a lot of plant engineers, project engineers in the plants are trying to work on water optimization. And it is important to understand how a low pressure system and versus high pressure system, how they are functionally designed and engineered. And for example, when you go to a low pressure system like a UF and MF, you will see that there are big pipes, and there are multiple CIP pumps. There are much bigger tanks. There is diafiltration. If you're making WPC, high WPC, MPC, protein products, you're having diafiltration water. And essentially, the reasoning for that all comes down to one major factor. All the UF and MF system, they have very high fluxes on CIP, high CIP fluxes. If you look at closely on the velocity, the flow rates of product, it's 600 gallons, 550 gallons, 450 gallons, or 150 meter cube per hour, 100 meter cube per hour. So the turnaround of these tanks have to be very fast. So the tanks are big. There are multiple lines. There are multiple valves, multiple pumps. And compare that to an RO machine. Same exact configuration, surface area wise, 9-stage machine, same number of housing, same number of membranes. The entire line is going at 120 cubic meter per hour or 550 gallons a minute during CIP, which means that the tanks can be smaller. You don't need multiple pumps to make this flow go around. Therefore, the amount of, and the reason why, like I said, it's a perspective that we wanted to share, that when you look at a UF and MF, you're going to see there are multiple ways you might be. An RO, for example, we gave you an example of recovering the CIP rinse. So there is some, you can say, like low-hanging fruit. There are some opportunities here, but the way you approach a water savings in a membrane system differs between low pressure and high pressure system. So that's the perspective we wanted to share today. And we believe that it's very important to understand this basic fundamental difference between low pressure, high pressure. Coming to seal water reuse, this is something that we found a lot of excitement actually when we walked into plants. We see a lot of maintenance team. I have caught on to the opportunity to recover the seal water, reuse the seal water, and what we're proposing one way that we have done in the past and we have executed, and there are probably 2 or 3 ways to do it. But what we have done is we've put a seal water feed tank and a seal water recovery tank, and we essentially go and recycle. So we add water using water valve going into these pumps, and then the return from these pumps are going to the seal water return, and then they go back into the tank, and they keep going and recycle until you can put an instrumentation. This could be turbidity, this could be again conductivity, and you can say, now there is some leak or there is some conductivity rise and I want to go to the drain. So you go to the drain and you fill the water back up using level sensors, and then you keep reusing the seal water. And so there is, because when you talk about, especially when there are bigger systems, bigger stages, let's say 8, 10 stage, 12 stage, or 12, in some of you in different parts of the world will call it loops. When we talk about that, the number of pumps, the number of seal water, you can be using 1,000, 2,000, 3,000 gallons of water in all day if you keep going to drain. And so therefore, trying to reuse the seal water is highly valuable. Product displacement, or product flushing or displacement depends depending on which terminology you're comfortable with. This is another form where we wanted to give you partially a perspective and also ways to if you're looking to optimize in your plant, things that you have to think about and understand. So the example that we are using here is about low protein products like WPC 30 and high protein products like WPC 80 or WPI. One of the fundamental things, that difference between making these two products, is the concentration factor. So for example, here you have a much smaller concentration factor. Let's say you have 100 gallons coming in here, you have about 20 gallons a minute going on the concentrate flow. Or you can just change the units, but essentially it's 5 times reduction. Whereas for a WPC 80 WPI, it could be, for a WPC 80, it could be 30 times concentration, which means for 100 gallons, you only get about 3 gallons of concentrate out, right? So what happens is that essentially the concentration factor are widely different. So when you're displacing product out of the machine, that you will see that the amount of water that you need to use to displace the 80 product is much higher, because you have to keep the valve concentrated down and you have to keep making product spec because it has to go to the dryer. So the amount of water you need by the time you finish pushing out the product can be the amount of water volume, and the time you need could be much higher, right? So that's a perspective, right? To understand that it's very different if you have a WPC 35 plant versus a WPC 80 plant. At the same time, is what can you do about it? So one of the examples that we can talk about is the MPC process, like milk protein concentrate 70, 80, 85. A lot of times what people call is white water capture or white water rinse, which means they would open the valve wide open and just push the MPC product out, but instead of going to the dryer or capture silo, instead of going to the dryer and worrying about product spec, they would just bring it back to another capture silo and bleed that low spec MPC back into the next day's skim milk production 4 to 5 hours after CIP. So it's about opening the valve, pushing the product, forgetting about the spec, capturing it and reusing it. So that is one way. That is one way the MPC application has that we've seen. But again, our goal here was to give you perspective and try to see if this is an issue for you, if you can try to find out ways to optimize. Now, like I said, we have to talk about RO water because we are talking about water. Just checking on time. I think we're doing good on time. So RO water, like I said in the introduction, RO water is something that as an industry, I think we've done really well, right? Like everybody, many of you are aware of RO polisher. Like this is an example of a WPC or MPC, let's say, and then you have UF permeate and you make like RO concentrate, you make 18, 20, 24 solids, and then the permeate from the RO is going to the RO polisher, and you can add some evaporator condensate if you have, lactose permeate streams. So, but the RO water that we're talking about, people are aware of RO polisher. What we did is we went and said, okay, there is good understanding by the industry about using the RO for water recovery. What can we do? Add in more, right? So what we did is we said, okay, let us see if you have an RO making 18 solids, 21 solids, and 24 solids. And when I say RO making, I'm talking about not of the RO polisher. I'm talking about the RO before the RO polisher, right? So if you make 18, 20, 24 solids on this particular RO right here, RO concentrate, right? So automatically, the higher solids you make on the RO concentrate, more water you're going to generate out of the RO permeate. So what we noticed is, let's say you go higher and higher in solids for the same feed rate. And if I recall, it was probably like 130, 140 cubic meter per hour, which is probably close to like 500 gallons a minute or so. But if it's like you need a 7-stage machine to make 18 solids, let's say you need an 8-stage or 9-stage or a 9-loop machine, and you need 11-stage or 11-loop machine, right? But overall, the important thing that we are presenting here is water recovery. After using the water to CIP these particular extra 2 stages, what we've noticed is that if you make higher solids on the RO, the preceding the polisher, then because of the more water coming to the RO polisher, we're able to easily make about 15,000 gallons extra than what the RO polisher would have anyway made. And if you go to higher solids, then you have a potential to make 20,000 gallons of extra water in a day, or 77 cubic meter in the day. After, this is more than the baseline. Like there is a base case, and then you're making extra water beyond the fact that you have stages and extra membranes. You can have excess water, and then of course, I'm not talking about the processate, citric acid, the usage that you might need if you're going higher and higher solids. That goes along with it, but it kind of depends, what is your need. We're presenting this on behalf of water recovery, so we're presenting that angle, but definitely energy, acid addition, all needs to be factored in. The other point which we don't have as a slide, but I'd like to share, which is about RO polisher, recovery of RO polisher. As an industry, that what we have noticed is that I would say maybe 10 years back, everybody was doing 90% recovery of water, which means you have 100 gallons go in here, you have 90 gallons of water coming here and 10 gallons going here, or let's say 100 cubic meter, you'll have 90% of water coming. That's 90% recovery. A lot of people are used to terminology of 10x concentration factor, which is the same as 90% recovery. I would say in the last 4 or 5 years, definitely more and more plants are trying to do higher and higher recovery. So we often see between the 92, 93, 95% water recovery being pushed. Maybe 20x concentration factor, which is same as 95% recovery. So that's where the industry is today. There are certain challenges that do come up when you go higher and higher recovery. Our thought process there is it really depends on the minerals content or the quality of water that the RO is getting fed in polisher. So in some plants, you're able to see comfortably making like 20x concentration or 95% recovery, whereas some other plants have more rigorous CIP in order to overcome that. So that's certainly something which is probably subjective is where we are today. But certainly there is a push in the industry in the last 5 years. What we have noticed that there is a push to increase the recovery from 90 to 95. And I think maybe there are people who are doing more than that, which is excellent. But that's just something we wanted to point out, that we generally see a trend to go higher and higher recovery, which comes with its own compromise. But it seems like there is a solution workaround that is going to be feasible, that we're going to see across the industry. The last topic about is DF water optimization. So for those of you who are newer to filtration or dairy filtration or protein filtration, DF water is the water that's being added, say, to a UF machine in order to it's added to make higher protein products. It's essentially water that's being added. You can add like polished water. Of course, after UV or after chlorine dioxide treatment or other treatments that might be more regulatory standards to where you're from, use that water and add it in the UF machine, and you can make high protein products. Now, what we are suggesting here is it is important to understand where the DF water is added. For example, a 9-stage machine, like if you add the water from the stage 1 to stage 9 or stage 6 onwards or stage 4 onwards, and the amount of water you use in each option defines how much water you will use. Now, saying this, I would say this is generally probably a fairly well understood concept, that you have to add water more and more to the back end of the machine, which we are adding here 6, 7, 8, 9, and that gives you the best water efficiency, best amount of DF water optimization. But certainly take a look at your plant. If you see there is opportunity, try to see if you can move that water to the back end. And the second thing goes without saying is also about where you inject the water. I think a lot of over time, I think people have learned that adding to the suction side of the stage pumps are very effective, but certainly that's something that you can pay attention to. But there are a couple of things, where and how you strategically add water and how mechanically you're adding water. So coming to this is the last slide. We have a couple of minutes. So before we go to the Q&A. So the topics that we covered, CIP, rinse, and rinse recovery. So if we pause here and understand, because there are multiple subdivisions here, we talked about using valve. We talked about using instrumentation and trying to go either to the drain, and after some time, when we feel the conductivity is low enough but not completely low to the water, we can say we capture that as a caustic recovery or acid recovery. That I'm going to say, let's say like 60-70%, it's rinsed out well, and now you capture it and reuse it for next day's caustic or acid strategically. You can't just use it in the first wall. You can't use it in, you have to strategically choose when to use that recovery caustic and recovery acid after doing some extra chemical addition. Then we talked about also, let's say, using instrumentation wisely. You can use with existing flow meters possibly, or add instrumentation, because they're fairly economical. But what we talked about is an RO machine, let's say a 9-stage machine, and you don't have multiple valves like a UF and MF, which you can isolate a stage and rinse only a stage 2 or 3 and not 4. In RO, often you're rinsing all the stages at one time. And even if you slow down the pumps in the front end, 3-4 minutes for a 10-minute, let's say, rinse, 3-4 minutes down the rinse step, you might finish rinsing, but it's still rinsing. So use the flow meter or instrumentation wisely and blend that permeate from the first few stages back to the permeate tank, which again comes back as fresh water for the later stages to rinsing. So instead of going to the drain. We talked about SelRO. I know we briefly touched upon it, but if you're interested in recovering your entire chemical, which I gave an example of an evaporator, you caustic, if you want to recover the caustic, we have many installs we've done for decades now. Reach out to your regional person, sales manager, and they will try to do an ROI calculation and see if this is a wise option for you. Depends on the chemical cost that you're paying, supply chain, the wastewater treatment. So there are a few factors need to be looked at. Chemical recipe or regimen, we talked about how Mike and I, we've often seen that for the same product, we've seen that people are using slightly altered chemical recipes. Work with your chemical supplier, see if you can be able to make one wash irregular. I took an example of acid step on a WPC 80. It could be a caustic step on a permeate RO system. Work with your chemical supplier, see if you can optimize that and make it alternate day or weekly once or twice. And other things, definitely, I know our CIP partners and your CIP suppliers are in touch with you, but certainly try to see if this engagement gives you any benefit. I'm sure, they have their tricks and ideas around these too, so they might be able to share very specific information, and we're giving you an idea. So low pressure versus high pressure system, we learned about the perspective on how low pressure systems like UFMF have multiple lines, multiple CIP pumps, DF lines, and more valves, and all because the CIP fluxes of UFMF membrane is maybe almost four times higher than an RO kind of membrane. So you need bigger tanks, bigger lines on a CIP of a UFMF versus an RO and NF nano machine. So when you are trying to do optimizing recovery of water, look at it when we're keeping that, having the lens in mind. It gives you perspective on how do you go about and do optimization. Seal water reuse, we talked about this, like we have operations where we're reusing the field water reuse. It gets a lot of water usage happens when you have multiple pumps. Certainly, we think you can save, 1,000, 2,000 gallons or more. And if you have bigger systems, even maybe 3,000 gallons, almost like 10,000, 15,000 liters. Product displacement, product flush, we learned about how making low protein products versus high protein products, the flushing step or the displacement is very different. And you have to keep in mind that when you make high protein products, you have to keep the valve closed for a longer time. It takes a lot more time and water to push out the product displaced completely. So we gave an example, or about how people do it on MPC milk protein plants, where they open the valve and they don't worry about the product spec, and they just blend back the low spec product into next day skim milk, by blending it in 4 hours, 5 hours after CIP, just blend it back into the feed tank. But certainly there are things there that can be looked at. RO polisher, you can't skip RO polisher when we talk about water recovery. We talked about how going higher solids can generate more water, and there is opportunity there. We talked about how recoveries of polisher systems as such is trending today. DF water optimization, that was the last slide we shared about strategically knowing where to add the DF water, mechanically check and make sure you're having water added the right way, having good mixing with the product. So with that, I'm thank you so much for, I guess, giving us your time. We know your time is extremely valuable. Busy schedules, 45 minutes, 1 hour is a lot of time. So we thank you so much for your time, and I'll leave it back to you, Emily and Mike.
Thank you so much, Saagar. Appreciate that. Just as a reminder for those who maybe joined a little bit late, within the next day, you'll receive an email from Kovalus Communications. We'll have a PDF technical white paper of this topic summarized, that everybody will have access to. It'll have the same graphs and information. So you'll be receiving that. I'll have other resources as well. So as Saagar said, thank you so much for attending. This is the first webinar, and we'll have more topics to come in the future. For those who want to stick around, we're going to have a Q&A session right now. So if you have any questions that you want to post to the team, put it in the Q&A area. And we'll take the last few minutes here to go through that. So thank you so much.
Thank you, Emily. So unfortunately, we don't have too many questions right now. I guess the audience has to digest all the content presented by Saagar in this very short period of time available. But let me ask you a question, Saagar. You talked about the seal water recovery. Is it needed to clean this whole circuit of the seal water in regular frequency?
Yeah, I think I mentioned it the last time when I was talking about it in the last session we had of this webinar last week. You're absolutely right. This is definitely has to be CIP. I can go back to the slide, but essentially what we did, Mike, if I recall, is we put a pulse valve going to the seal water tank, and every time during the CIP wash, the valve will pulse, and then the seal water tank and seal water lines were getting CIP. So it is actually very critical to clean that line, because everybody knows when we do recycle of anything, in this case it's water, any recycle anything in any operation, any food, dairy manufacturing operation, any recycle creates you're susceptible to microbial kind of situation. So certainly the seal water lines have to be CIP'd along with the whole system without a fail, because we're not going to drain the whole time. So yeah, thanks for bringing that up. Good catch.
Very good. Thanks for your answer. Another question is concerning the product displacement. You explained us that the control valve for the concentration factor for the high protein content streams needs to be closed for a long time to keep the dry matter level constant for the dryer. But there are systems, at least I have seen, where's the bypass valve around the control valve. Could this just be used for doing a quicker flush out?
I mean, if opening a bypass valve, I suppose, is the same thing like opening the ratio valve, right? Or the concentrate valve or the ratio valve. So it's the same thing, but the bypass valve is again on the same line, unless I misinterpreted that. So it would be the same thing as opening the ratio valve itself. So, but going back to thinking about the topic a little bit more, now you bring it up, is one thing, of course, often, let's say you're making like a WBC 80 or something, you can make a higher protein product all day, and then let's say you make like WBC 81 or something, and then you can essentially open the valve and push out faster, and you end up eventually diluting. But this is all works out only if you're all going into a silo, right? But it's not the case if you're directly feeding into the dryer. So it's sort of tricky how you do it at that time. But I guess to answer your question, yes, the bypass valve will help out flush, but I think it will still end up being reducing the product spec. You're going to sacrifice the product specification somewhere.
So that would only be an option if you're sending your material to a silo and reuse it during the next day's production as a feed material.
Yes. I guess that was the MPC application we're talking about, that you open it and reuse it the next day. But yeah, if you are having a big silo ahead of your dryer, though, then you don't have much of a worry, right? You can just you can make slightly higher spec 80.5 all day and just push everything into it and make it average out to 80 before it feeds the dryer. But that's not an advantage that everybody has often. So yeah.
Okay, thanks, Zara. There's one question now just came in from Josh Hoover. And he's asking if during the plug flow flushing, if there is let's say, the chance that the membranes are seeing pH thermal shocks, and if this could jeopardize the membrane integrity.
I mean, I think it'll be interesting to know if I know we were talking about activating the voice, if the gentleman can talk to us and we can ask some questions, but I guess in some of a lot of products that I know, Mike, you and I work on is like pH of 6 or 7 or in that range. So the water, even if it's like plus or minus 1 pH, it's not heavily altering any. I think this almost it goes back to when I think about shocks and pHs and temperature. I actually think about ceramics first, right? You know how ceramics have that slight susceptibility to change in temperature shocks, and so I don't think they have as much of a pH shock, but they have a temperature correction shock. You have to go slower and not. Maybe let's assume theoretically, hypothetically, that the product is, say, pH of 12 or pH of 2, and then you're trying to do that. You're trying to take pH of 6.5 or 7 water and try to do that. I actually don't feel that the spirals are that. Because the pH range of spiral membranes are, they are good between 2 to, we generally do 2 to 11.5 or 12. So I don't think in that range that the spiral membranes are that susceptible, because we often do acid rinse or caustic rinse, right? Where we are going from pH of 1.8 or 2 to pH of 7. So we have not seen, and these membranes are lasting 12 months, 18 months, and sometimes longer. So I don't believe, no, I guess my answer would be no. I believe that the shocks are manageable for spiral membranes.
And if I may add something to this regarding temperature shocks, of course, if you have been running a high temperature CRP step with temperatures up to 70, 75, or even higher.
Centigrade, yeah.
Centigrade, yes, sorry. Then of course you should not try to lower that temperature instantly from 70 down to 50, because that of course could long-term jeopardize the membrane integrity. But if you have SIP rinse cycles where you operate at 50, 55 degrees C, then there is no issue with changing the temperature very rapidly.
Yeah, and I think the heat sanitize. I know one thing. I think the knowledge about heat sanitizing our membranes sometimes gets missed. I would say as a common knowledge. I think it's available. A lot of people know it. But certainly, if we could at 70 C, you're talking about probably high temp membrane. I'm talking about heat sanitize. I guess that is completely different. But on high temp membrane, I have a follow-up to ask you. I think you have worked on projects which are using high temp CIP or high temp membranes. Are you running lower pressure drop when you're doing the high temp membranes, or is that something that when you're in high temp membrane, you're not doing lower pressure drop? Because I know lower pressure drop is so important when you do high heat sanitize, which I've been part of many times.
Certainly during hot water sanitization steps, of course, the cross flow velocity / the pressure drop along the spirals needs to be reduced for sure.
Yes.
And also during high temperature CIPs, also the delta P's need to be reduced, but not as much as for during sanitization steps.
Okay. That's good to know. I was not familiar on the high temp because there's not too many projects I've been part of as much as you. So that's good to know. Thank you.
The use of HPHT membranes, which is how we call our membranes. Other membrane suppliers call them differently. They are widely used in Europe and not so much as far as I know in the US. That's correct.
It's available, but not as wide, I would say.
How are we in time, Emily?
Yeah, I think we're about 10 minutes over, so we can wrap up today's session. And if anybody has anything else, just put it in the chat. But I think, that's good for today. And thank you guys so much for being here. And we'll be in touch with you shortly with the email with the PDF, either this afternoon or early tomorrow. All right, everybody, you have a good day. Thank you so much.
Thank you, guys. Thank you for your time.
Thank you. Have a good day. Bye.